Okay, let's continue with the discussion here. So we have our flask. We open up the valve here to let the ideal gas go into the empty evacuated flask. And so to make things simple, we got three states that can be formed. And so we have state A, where all the particles are in the left flask. State B, all the particles are in the right flask. And state C, we have the four particles divided between the two flasks here. And so now we're going to look at each of these possible states and look at the microstates. So here we have state A. So the macro state A, all of the particles are in one side of the flask. And so to look at the possible microstates, we're going to identify each of these particles and we're going to label them 1 through 4, right? So it doesn't matter which particle is 1 or 2 or whatever the case may be. But here we're going to label the particles 1 through 4, so each one has a number. And so when we're looking at microstate A, so the microstate A, all the particles are on this side here, all 4. And so we can label these 1, 2, 3, 4. It doesn't matter which spot that they're in, it's all going to be the same anyway. So we have 1, 2, 3, 4. And so here we only have one possible microstate since all 4 particles are on this side of the flask. And the same thing with macrostate B, where all of the particles are on here. And if we look at the microstate and look at what the positions are of each of the particles, assuming that it doesn't matter which spot the particle is taking, all particles are on this side. So 1, 2, 3, 4. So this is a 1 microstate here. So here then, for both microstate or for both macrostate A and macrostate B, both of these only have one possible microstate. But if we look at macrostate C, where the 2 particles or the 4 particles are divided between the 2 flasks, here we can again label each of the particles are labeled. We can see that we have different microstates that fit this macrostate energetically speaking. So here we could have particles 1 and 2 on the left and 3 and 4 on the right. Or here we can have 2 and 3 on the left and 1 and 4 on the right. Or we could have 1 and 3 on the left and 2 and 4 on the right. Or 2 and 4 on the left and 1 and 3 on the right. Or 1 and 4 on the left and 2 and 3 on the right, and 3 or 4 on the left and 1 and 2 on the right. So here we have 6 different microstates that match up with this macro state where the 2 particles or the 4 particles are divided evenly between the 2 flasks. So we have, depending on what particles are there, right, 1 and 2 are on this side, or 3 and 4. So by labeling the particles, we can see that this is a different microstate than this, because the over here we have particle 1, but over here we have particle 1. So 1 is on a different side. Here we have 3 and 3, but 4 is over here. So here between these, we switch 3 and we switch 4 and 1. So 4 and 1 are switched for here. And we can look at the others here. But the important thing to remember, to keep in mind here, is this macro state has 6 times the number of microstates compared to these two. So as far as probability goes, this has a larger statistical probability of winding up in this form, in these microstates, or in this macro state, because there's more energetically equivalent microstates or ways to arrange your particles that fit this macro state compared to these two, right? So there's a greater probability of being in this state here than in these. And so this is more likely to happen than these two here, even though they're energetically the same. This has more of a higher probability of being in this position or in this state here. Um, and this stays the same, or you could see the same thing happen if you increase the number of particles, right? So if we increase the number of particles to 10 atoms instead of 4, then we increase the number of microstates to 252 for macro state C. These macro or the microstates for macro state A and B stay the same. They only have one possible microstate because these macro states are where all of the particles are on one side or the other, and that's only one microstate possible for that. So as we increase the number of particles, the number of microstates for macrostate C increases exponentially. You can see that if we increase the number of atoms by 10 and we divide them evenly between the two flasks, that would give us 252 of these microstates. If we increase that to 20 atoms, where the 20 atoms are divided evenly between the two flasks, then that would increase the number of microstates to 184,756, right? So as we grow the number of particles, the probability of winding up where the gas is evenly spread out or evenly divided between the two flasks grows by a lot, a huge amount. And so this fits with the what we talked about with regard to the second law of thermodynamics, because remember the second law of thermodynamics says that a process is going to be spontaneous if it increases the entropy of the universe. And we can see here that entropy again is related to the dispersal of energy, and you can see that here compared to here and here between these macro states and this macro state here, the energy of the particles is dispersed throughout the tube. So it's more dispersal of energy here in the tube compared to here. And that's also tied to the fact that we have more microstates. So remember the formula that we were just talking about a moment ago, right? So the S is equal to Boltzmann's constant multiplied by the natural log of W, which is W is the number of equivalent energy equivalent arrangements of particles. And so here we have a greater number of arrangements of particles that are energetically equivalent, and that leads to more entropy, an increase in the entropy of the universe. And also you can see that there's a dispersal of the energy. So the more particles you have, those particles contain the energy of the system, and as the particles spread out or expand into wider spaces, you get that dispersal of energy because the particles are taking the energy with them. So as the particles spread out, and so does the number of so does the energy, and that also increases the number of microstates that you can have for a particular macro state. So I hope this is helpful for understanding entropy in relation to the second law of thermodynamics and how that relates to microstates and macrostates and all of that. So if you enjoyed this video or my last couple of videos, please make sure you like the video, subscribe to my channel, hit that notification bell right up there so you can be notified by other videos I put out. Put a comment down in the comment section if you have a question. I'd love to hear from you. I like answering questions, and I like to hear from my subscribers and viewers. So thanks for joining me. Have a great day.